Good morning, everyone. It's a pleasure to be here in Natal in this nice meeting. I'm learning a lot from the part of heat transport. I'm more like from the electronic part. Sorry. Oops, wrong buttons. Today I'm speaking more about electronic transport, and so this is the complementary part of the workshop. And I'll begin with showing you my plan. I'll say a few words about advertisement, about the posters of people from my group who are outside waiting for you to visit during coffee break. And I'll give just a teaser, and that will be 15 minutes. And then I'll pick up with things that Amon talked about, and also Alexandre Rocha, and I'll emphasize the importance of interference phenomena in electronic transport. And what I find very interesting in this meeting here is that since once you talk about phonons, so you're already dealing with things with their waves, right? So you start with waves. And here, there is this duality between waves and particles in electrons, and decoherence plays an essential role for everything we talk about being of interest in quantum transport in electrons. And this is going to be sort of a review for people that know it's an old-fashioned thing, but it's good to from time to time to revisit. And then I will begin with the technical part, which is basically I'll talk about the mechanisms and the formalism, and I'll review some of the single particle and many body problems we're interested in. And we are people working with non-equilibrium Green's functions, so this is going to be a big part of the talk. And then I'll focus on the last part, which is essentially the main topic of the talk, and it's a very special problem that we have been addressing, studying, working on over the last few months. Okay, so the first post I want to advertise has some relation, and probably a strong relation with the previous talk, and it deals with spin-orbit interactions, and it's a little bit of a different kind of what has been discussed here. And so it's a quantum spin Hall effect due to add atoms in graphene. Graphene actually was part of this debate on bending or not bending. So we do know that planar graphene has a very weak spin-orbit interaction. Carbon is a very light element, so we expect it to be very small. And then in order to play with a spin in graphene, to do interesting things in graphene, people envisage ways of either depositing graphene over a substrate or adding add atoms, which are heavy, and then the spin orbit is strong, and then by causing some spin selectivity. And this is kind of old. I mean, the idea of spin Hall is kind of old, but quantum spin Hall is not that old. And the idea of, it's pretty much like the Hall effect. If you have a magnetic field and you have electrons flowing one direction, then due to the magnetic field, the electrons will bend. There will be charge accumulation in one side, negative carriers, and positive at the other side, and you have a Hall voltage across the sample. So in the spin Hall, things are a little bit more complicated, or more interesting, let's say. For instance, if you have a spin orbit, the spin orbit can be cast as some sort of an effective magnetic field that will act in one way if the spin is up and the other way if the spin is down. So if you have a flow of electrons in this direction, some of them will go that way, some of them will go that way, and then you have a spin imbalance at two sides of your sample. And this is something you can measure, and this is something you're interested in. And so the inspiration for the work was this so-called giant spin Hall effect in graphene. And here the experiment is basically you have graphene, CVD graphene, grown over a copper foil, and the copper will do the magic of bending the trajectories of different spin species in graphene. And then you shoot let's say, a current through that direction. And then depending on your spin polarization, electrons will flow that way or that way and not going straight to the other side. And then you can measure the non-local resistance here. And from that you can infer what kind of a spin orbit or what kind of spin Hall effect you have in these devices. And well, there is a lot of into the technicalities of the experiments, and this is a very interesting paper I recommend for people that are interested. So our approach to that problem was basically, we do have technology in our group of doing the so-called recursive Green's function technique. It's a numerical method, and basically we start off at the transmission formula, which people have seen it several times with different names here. And this is basically, from that you can write a Landauer formula, but basically the transmission you can cast in that way. This is the Green's function across the sample, and these are sort of the couplings to different leads. And if you have a Hall bar, you have many leads, and then at least 4. And then that requires a little bit of, let's say, generalization of the standard implementation of the method that deals with 2 probes. And that was a major achievement by Leandro, who actually invented a multi-probe slicing system, and he can design any geometry, how many leads you wish. And from that, you can compute the transmission, the local density, local currents, and different kinds of observables. You can attach STM tips if you wish, and do different neat tricks. And so I don't want to spoil the fun, but he will be happy to explain to you all the details. And basically, he starts with a Hall bar, and he throws some concentration of impurities, and going from very little to, unrealistically large concentration of heavy elements with spin orbit. And if he shoots the current in one of these lags, one of these terminals, what you can see, let's say you shoot a spin polarized current in one of these lags, then the spin orbit has this property of selecting the spin and bending over to this part. So some of them is transmitted across, and there is this asymmetry generated by the spin orbit interaction. Depending on the concentration, you can get more and more until you get to a regime which is actually quantized. It's like quantum Hall. All the current crawls along one of the borders, one of the edges of your system. So this is the nicest picture I have to show, and the remaining results Leandro will be happy to discuss with you. Good. So the other poster of our group is non-equilibrium Green's functions for phonons, and comes under the name of heat transport due to phonon steady state and pumping, and that was done by Marconi, who is sitting also here, and Leandro as well. Good. So what's the idea? So we wanted to actually use our knowledge on non-equilibrium Green's functions to understand or to investigate heat transport. And so we know that this formula has been derived in several ways, and it was beautifully reviewed in one of the lectures, classically with quantum Langevin, and including non-equilibrium Green's functions. And that was our starting point. And then we consulted one of these reviews in this field, which is by Wang and Liu. And they have written another more recent review 2 years ago. And we were intrigued, after working after some time, we were intrigued by one of the sentences of this review, which says that we can obtain a symmetrized expression with respect to left and right lead and make it explicitly real. And so they pick the current and they add the complex conjugate to the current, and the current is usually a real beast. And so we investigated their expression for the current, and actually there is some flaw, and it's not, it's complex. And so that was the starting point, and so Marconi fixed that. So there were some small mistakes, and that gave origin to this work, and we extended it to treat pumping by also adding, let's say, to the system periodic external drive. So why was it important to fix these things and not to take the symmetrized thing? Because, well, actually, we believe in the Landauer, is because once you deal with pumping with NEGF, then the current, if you're not careful, then the current is imaginary, and you don't have this sum rule, because left and right currents don't need to be the same. And so you have to do something better. And so he developed analytical expressions for corrections in power of a small parameter that multiplies the external drive. He has current, heat current, also expressed in this parameter as the power. And the idea is to study cooling and heating. And all this you can play with, implement in simple models and compute things and show trends. So this is in the poster outside. So, okay, good. So let's move on. Let's go back to main track. So what I want to discuss is mesoscopic electronic transport. And in about 20 minutes, I'll begin to address a problem which is very non-trivial in this respect. So the key element here is quantum interference. And this is, let's say, a view of a quantum dot, a lithographically grown quantum dot, where one would say that, like a theorist, or the way you analyze is, you think of a billiard-like idealization. Electrons come from one entrance. This is the source, and this is the drain. They dwell for some time here. These are classical trajectories, if you wish, and eventually they come out. You can make it a little bit better. You can attribute to each of these trajectories a phase, and you see, and then immediately you realize that the interference about the infinite trajectories, that interference pattern that emerges from the infinite trajectories that can circulate here will give rise to your transmission. You can also compute it as well. So you can do it semi-classical, you can make a statistical analysis, you can compute via, for instance, recursive Green's function. The experimental realization, one always have to keep in mind, is some heterostructure where actually the 2D electron gas sits here underneath. So these metal plates here are gold or some other metal, and they are far away they are not, let's say, in contact with the 2D electron gas. But if you have some kind of a gate here, you can tune some potential that will actually shape or constrain the trajectories of the electrons to actually follow something like a billiard-like idealization. So there was a lot of activity in late 90s or early 2000 concerning this correspondence between the classical quantum picture and also the quantum transport in these beasts. So what did we learn about it? And so this is an easy explanation. And so here I regard electrons as particles, but then I attribute some probability and amplitude for a particle to go from A to B. And this can be a sum over different possibilities or trajectories that it will have. And then, you know, a simple exercise, if I think that there are only two trajectories that are possible, I forget about all the other possibilities. The transmission from A to B is basically these beasts. With two trajectories, you have green and red. And so this will be the classical, you sum probabilities, and this will be the quantum interference where you're sensitive to the amplitudes. So, in terms of, let's say, transmission or resistance, you think about a classical circuit theory where you have a QPC, a constriction here, a constriction there, and then the conductance, which is just, well, this is what we learned in high school, will be written in this way. Let's say that every one of these constrictions has a transmission which is proportional to the number of open modes that you have. And by the end of the day, doing a hard theory, what you learn is that the quantum corrections to that are just of order 1 in these units, plus, and the total transmission, total conductance is just the classical plus the quantum, and the quantum is of order 1. And this is kind of a robust and universal result. And so there are a lot of activity computing this one over many years. So, and then you say, why should I care? If n is large, then this one is an insignificant correction to that. So all this is interesting when you get really small devices where the number of channels is 1 or 2. And then the fluctuations, they are important with respect to the average. And so there were several experiments in the late 90s that will show that these guys really are of order 1, sometimes a little bit smaller, sometimes a little bit bigger. And another important, and what I wanted to say, which is also important, is that this pattern is not noise. You measure one day, you measure the other day, is the same, unless it's a very sensitive experiment, unless your experiment goes wrong. But if you, it's a very stable over days, depending on your dilution refrigerator and fluctuations of random charges in the substrate, etc., etc. So this is not noise; it's just quantum interference. And the other interesting effect in that is the so-called weak localization. And the idea is that if you have a trajectory shooting into one of the system like that, they have a maximum of interference or a maximum constructive or destructive interference if you think about the time reversal conjugate. To this yellow one, there is always a red one which matches and they interfere perfectly. And so what people learned is that there is enhancement, a quantum enhancement of the backscattering. So this is the semi-classical prediction. Once you put a perpendicular magnetic field, what happens is that these phases no longer cancel each other because accumulating phase that way or that way is different, and the effect goes away. And that is a very hard experiment in these things, but it has been done. People have produced several devices, and the average over the several devices is this, let's say, this curve, which has a given shape, which has been predicted by random matrix theory or other theories. And the other point is that, well, the deep of this correction is too small, or I mean, one would expect it to be larger. But then comes the other thing that I wanted to emphasize in this talk, is that electrons are, they couple to the environment. And in particular, if you are in these cavities, if you want to, these effects, they depend on longer and longer trajectories. After some given time or after some given length, there is always a chance where one electron is influenced by the other electrons. This is single particle theory. And then the phase that you have in mind in a single particle picture no longer holds because you have to account for other things in the environment. So here, to the disappointment of the audience, this is a real very small temperature. This is done at sub-Kelvin and sometimes 75 millikelvin, 25 millikelvin. Here phonons are of no importance, or at least density of phonons is so small that the other effects take over. And so it's more like a many-body collective or electron-electron interaction dephasing. And that explains this suppression of this peak, and we have done some work in the past, long time ago. Good, so the picture that I want to show you is very simple, and again, let's think for a while that our system is ballistic, so there is no electron impurity mean free path, okay? So you have a very nice and ballistic system, and if your coherence length, I mean the length it takes to be scattered by another electron or something that is beyond your single particle model, if this guy is longer than the size of the system, you are really purely quantum. So things, even if you are diffusive, I mean, you might have all this stuff here, but you are still quantum. So once the coherence length is smaller than the size of your system, then you can only think that you are quantum over patches like that, and then you have a sort of network of quantum resistors. And so all your effects, all your beautiful corrections, they go away, and depend actually on this ratio of L phi over L, which plays a role. And so this is a thing that is a major difference from what we are thinking, what we are hearing during this week here. So L phi is an important thing here. Okay, so this is all stuff. Let's move on and slowly come to what I want to address. And what I want to address is that within the single particle picture, people have really done a lot of things and understand pretty much. I mean, we can qualitatively explain almost all experiments in that, and we can make very nice models, keeping the essence of what we learned from these experiments. And we can also be quantitative if you like. Sometimes you can be actually very quantitative in that, and there was a big effort towards that. So where things become a little bit harder is when you actually have to do with many-body effects. And so for that, well, I explain more what I want to say. So what I have been discussing with you so far, and so far no spin was at play, but it will come. So was this situation where I have a wide open system. So a quantum dot is very strongly coupled to the external world. And then you can think, I mean, and then you have all these fluctuations. This color code refers to the conductance in units of E square over h, or 2E square over h, I don't remember. This is the perpendicular magnetic field, and this is a gate that basically will vary, let's say, the Fermi energy, if you wish. Okay? What happens here is that you can think of the system almost like a fluid, you know, like the electrons flowing, and there is nothing to prevent charge of going inside or outside of your system. So there is no real big control here. Charge flows all the time. So if you measure for any kind of time what is inside, you have some average thing. It fluctuates a lot. Good. So there is the other very limit where basically you put very large constrictions here. And then what happens if you put these large constrictions, you know, like it's weakly coupled, so things dwell a lot of time inside. And essentially the system starts to realize how many charges it has. And because an average is a definite number. And then what happens is that if another electron wants to come in, it has to pay a price because there is a charging energy. There is a capacitive charging energy to load another charge to this dot. And so all this V gate, this external gate, is essentially telling us that you have to move on or to supply some, give some electrostatic energy to your system in order for these guys to circumvent this barrier and populate the system again. And then you have all these resonances here, isolated peaks. Everything is overlapping, and here is isolated. And this is the so-called Coulomb blockade regime. So you know exactly what condition you have. N and n plus 1 is you know, like say both are equally probable, so you can tunnel in and out, and transport is facilitated under the circumstances. And then there is this regime, intermediate regime, where everything is more complicated. So how do you make this transition from here to here? And this is the most difficult thing to address for a theorist. And so these are the open quantum dots. The Hamiltonian is bilinear, like everything we have been discussing so far. Here it's a Coulomb blockade. In principle, it's a many-body problem, but you can actually there are ways to do perturbative expansions to explain it simple. And here is a non-perturbative thing where you have many-body correlations all over the place, and this is the harder part of the story. Good. So let's move on. So and then the way to start is to have a very simple Hamiltonian, right? So let's consider the simplest thing you can ever imagine. You have a dot with a single level, and then you can have either one electron here or two. And if you have two, then you have to pay this price of having two electrons in your system. There's a charging energy that I described here. Or you can have 0, 1, or 2. That's the idea. And all this is described by this Hamiltonian that here's the single energy level, and here you tell us, this tells us what is the charging energy. This stands for the leads, which are modeled in principle by a wide band, and this also stands here for the coupling. Good, so this is the simplest model of what was put forward by Anderson, Phil Anderson, in the 60s, I guess, yeah. So, and it has been addressed by several people since then as a workhorse for this problem. Good. And then how do I compute the current, right? And here comes one of the technical parts. And you've seen this formula, but you probably don't remember. That was shown by Alexandre on Monday or Tuesday, on Tuesday. And this is the formula that you get for the current by doing a rigorous calculation of, starting with the Hamiltonian and deriving what will be the current in a situation where you can be out of equilibrium. So in addition to the standard Green's function that everybody is familiar with, there is this guy here, which is the G laser, which contains most of the information about non-equilibrium. And this is a guy that is very hard to compute. I mean, not in single particle, but in many body, this is hard to compute. And so you want to get rid of it. So in the 80s, people noticed that if you're in steady state, the current flowing from the left lead is you have charge conservation, then is minus the current flowing from the right lead. And so people came up with the sum rule, and just basically adding things. And this gives you a good way to check if you compute your G lesser, if you integrate over the whole band. In principle, this has to be 0, and that tells you if you're doing a good job or a lousy job. But this is very little because it's a very, this information, you cannot make this guy 0. You have to integrate. That's a bad thing. So you cannot make that this guy is equal to minus the other side. And then there is a trick that was the part that Alexandre discussed. It was put forward by May and Wingren in a very beautiful paper in 92, 93. And in order to get rid of this guy, they assume, well, let's take a very simple assumption. Let's say that the two leads are equivalent, are actually identical. So apart from a constant. So they have the same energy dependence. That's the important thing. And if they have the same energy dependence, what you can do is that you can write this, you can play with this identity here, and you can get an expression for the current either left or right in terms of actually only the Green's function, the retarded Green's function. And then you have to integrate over this, and this is a way of summing things up in order to get rid of your G lesser. And that's a very smart trick because there are lots of methods to calculate G retarded in many body problems, but there are no very well-established methods to calculate that. So you have to do perturbation theory, et cetera, et cetera. but this is a very stringent hypothesis. So in the sense of a toy model, that's fine. But if you're dealing with molecules or something more sophisticated, or even things where you have, I'll come to an example soon, then this is no good. Okay, so that's an important message here. So how do you calculate this G lesser? And I'll bore you with some of these. But there is a very old method called equations of motion. If you define your time-ordered Green's function, you can take the time derivative of this guy, take the time derivative of the operator, and then do Fourier transform. You eventually end up with this horrible formula where there are two new objects here. One is this guy called gamma alpha Q beta, and the other is this G2. And there's two new objects you have to calculate, and every one of those has an equation of motion itself, and things tend to proliferate, right? And so basically, what people do is so in the next generation, there are these new objects to compute, and one thing that people do is, well, let's make a sensible approximation here. Let's try to truncate, taking into account the main contributions at different levels. And this is what people usually do. And so in the first level, you end up with a very simple expression, and very nice. You end up with a Green's function that has two poles and has a simple expression for the width. So basically, this would be the imaginary part of your Green's function would look like that. And that immediately allows you to compute the transmission, and it has an spectacular, let's say, agreement with all the scalings of what you measure. So this is let's say a sensitive, let's say, approximation for the Coulomb blockade regime. Okay, good. So and then you okay. So if you are successful with that, let's go to the next order and see if I do order by order. All of a sudden, you might think that you can solve the problem, and then you have to solve these beasts. And once you do equation of motion for these beasts, there are more and more objects that appear, and eventually there are correlations between operators that act at your leads, operators that act on your quantum dot, and all this stuff becomes a real mess. And that doesn't prevent people to go on with that. And but the results are not good because it's a series which has no small parameter. Actually, you wrote a nice paper on that, criticizing some of the truncations. Was in the early 2000, yeah, and so this is not a very good way to go. You can improve, but and it's better to do something smart in order to tackle the problem. And there are some of those methods, but all these methods they teach us how to solve the retarded Green's function and not really the lesser Green's function. That's the mess here. Okay, so what kind of physics do you expect in this situation? And this is the old, very old Kondo effect that plays. And I'll just highlight again. So all these vertices here, these coupling matrix elements, they refer to spins, and a sigma with a bar is the opposite spin. And all these guys, most of these guys, reflect some correlations of spin in the lead and the dot. So this is why I call this the emergence of correlations. These guys become more and more important, then you have a more correlated system. And that's the idea. So for instance, suppose that you have one electron in the dot. Suppose it's pointing up. So electrons this guy can go out, and one guy outside can be in, so you have a spin flip. You can also think about processes which reach some virtual state here. And all this, if you sum up all possible contributions to this process, the idea is that nature doesn't want to have an electron spin pointing in some direction. So the leads will tend to screen this state. and built up a very highly correlated state here to screen this single electron that is there. So if the dot is double occupied, even number of electrons, none of this physics happens. So it's just for the odd guys. Okay? When you have an odd, you have an unpaired spin that you want to do. And the scale where this happens is so-called the Kondo temperature. And you believe that if you are a temperature, real temperature larger than the Kondo temperature, then all these correlations vanish or tend to vanish. And if you have are at temperatures lower than the Kondo temperature, all this physics become very important. Okay, good. And its Kondo temperature has been expressed as a combination of these gammas, the charging energy, the position of the resonant level, etc., etc. Good. Okay, and so now this was theory. Now there have been about 15 years ago a sequence of papers where people were the first guys to measure these dots, and basically this is the physics here. For instance, say here you are varying Vg, you are filling up your dot, and this is a situation where you have an even quantum dot with the even number of electrons. So once you change the temperature, nothing really happens, or very small changes. Well, there is some change. But the effect is more pronounced if you have an odd number of electrons. Then whatever was a deep, these were the Coulomb blockade resonances, then everything is enhanced and goes up to this limit, which we call unitary limit. This is the maximum of the conductance you can get for this system. So just by changing the temperature, you can actually make the system conduct better here. And so this particular picture was taken from the last guy of this sequence, because these guys were accessing well, they were the first, so the experiments are less clear. So for a theorist, this is the picture. If you are in the Coulomb blockade regime, you see you have all these isolated resonances. Once you reach Kondo, if you have an odd number of electrons, the valleys are pronounced. Nothing changes here. The valleys are pronounced. And this is the thing. Good. So now we are ready to discuss my thing. And first an advertisement. So in order to develop some methods to tackle this kind of problem, simpler methods, then Bruno is working on dynamic mean field with Alexandre, who was here, but he's not. So Bruno has to explain the poster by himself. And so let's move on. So what I want to discuss in the last minutes of my talk is this problem that appeared last year, this experiment. And then you see things are, I mean, over the years have become far more sophisticated than the first quantum dots. You have a quantum dot. Look, you have a lot of electronics here. You can vary all these gate voltages, also what is called a cavity. So you have a quantum dot. Here is the source. Here is the drain everywhere. So electron comes in the quantum dot and then goes out either through whatever resonances that are there due to the cavity, or probably directly. So you have a typical interference pattern between different paths, if you wish. So one path is more complex. Electron exiting the quantum dot goes into, let's say, cavity states and then leaves, or it goes directly to the drain. And this is the interference pattern. What this guy showed, and that's the nice thing about this experiment, is that you can change a lot the conductance pattern of this quantum dot by just switching on and off the electronics of a thing which is 1 or 2 microns away from the dot. So you're switching a little bit things which are, let's say, far on the verge of L phi, which is the decoherence length. You can change by a whole amount whatever you have in the transmission here, and in particular the spin structure of this guy. So it's a way to manipulate by interference the spin structure of a dot sitting here. So this is the claim. Good. So So the experiment goes like that. So this is another illustration to help you a little bit to understand. Quantum dot sits here. Electron can go directly or can go over one of these levels of the resonance. And then if you are in a weak coupling regime, where say there is no Kondo, I mean everything is Coulomb blockade or cavity, then you see that there are these very nice peaks. Electron will actually, there is always a conductance here that tells you that electrons can go through to the reservoir, to the source, to the drain, sorry, without visiting the cavity. And there are all these resonances which are due to the cavity, and you can see them very clearly. And then there is this delta of the cavity, which is the mean spacing between the resonances in the cavity. And then what you can do is that, well, they are experimentalists, so, sorry. So you can just turn this gate voltage off, entirely off. So that means that there is no cavity anymore. Remember, this guy is sitting atop of the 2-DAG. So if you switch it off, then there is no barrier underneath. An electron can travel right away. And this is what they call cavity off. And then there is a very strange interference pattern here as well. So you have to understand that. Good? So in the regime of cavity off, then what you see is that you expect to see just the regular Kondo quantum dot Kondo effect. And let's say you have zero bias, no source drain, and that's what you see. You see that these bright regions correspond to a large conductance. So the dark regions are small conductance. So if you are even, you are at the valleys, and there is almost no conductance. If you are odd, then you have this enhancement of the conductance all over between the two peaks, and then you go down again. And then if your cavity is on, then everything goes like a little bit like crazy. And there are lots of things hard to explain. And this is another way to visualize it. Instead of changing source drain voltage, they change the cavity voltage, so they change the size of your system. Good. So, and all this is simple, and there are claims, but now there is, we worked a lot to have some quantitative explanation on that. And actually, on the way, we tried to fix this feature of the trick by May and Ringgreen. So that was. And so there were lots of people with different ideas, so we have to fight over a long time to get up with something that everybody agrees. So we have a simplest model possible. And again, the dot can go to the cavity or go directly to the drain, or and from the cavity it goes here. So this is our model. You have this interference pattern between these two paths. And then you have to model the cavity. There was a big discussion on the resonant levels of the cavity. I think I'll skip that. But and this is the scenario. So if you have just the dot and the drain, it's a simple thing that you just Kondo physics like usual. And if you have the cavity, then you have all these possibilities, right? So cavity doesn't have any real spin dependence, the levels here. So you populate 2 by 2. So the first number is the number of electrons sitting in the cavity. The second number, it refers to the electrons in the quantum dot. If you have an odd number of electrons in the quantum dot, then is where everything takes place. So you can have correlations between the electrons in the dot and the cavity, or correlations between the electrons in and the leads. And this is the competing process that you can tune on and off by a single knob. And well, let's do it fast. So some of our collaborators were very fascinated about modeling very precisely the cavity, and we got very interesting results. And we used this Quant project, which is also an interesting thing that you can discretize the whatever system you want and compute scattering matrices and transmissions, and it's an alternative to the recursive Green's function. And what we learned is that only the n equal to 1 mode, in, for instance, if you have system with cylindrical geometry, then you expect usual Bessel functions. Then it was a little bit like a surprise why just the n=1 mode contributes. And that explains a very large discrepancy in between the density of states of the cavity and the peaks that have been measured. And then if you think a little bit harder, then you realize that the Bessel function for arguments which are very small, it goes like x to the n. And so n=0 has the wrong parity, and you need only odd parities to couple this guy here at the entrance. And actually, it's very simple. So if you go to higher Bessel functions, then the wave function of this cavity is essentially 0 over a large extent, so you do not couple to the quantum dot. So basically, the guys that couple are guys like that. So different angular momentum, different angular momentum is the same, but different nodes. And these nodes correspond to the guys that you actually observe in the experiment. So now this is the most important thing from how we solve the problem. And I mentioned the usual trick to get rid of this guy is to do this. And I told you that once the two gamma functions, left and right, have different energy dependence, which is the case here where you have this interference. One is the direct coupling to the quantum dot, and the other is the competition between all the interference patterns. So gamma right contains all the interference patterns. So it has a very rich energy behavior, very much different from that. And so this doesn't work. And so we have to analyze how this G Lasser behaves. And then we found out that, at least going order by order, two orders, first and second order, we realized that this derivative with respect to the chemical potential behaves like the derivative of the Fermi function times a very complicated function that is smooth in energy. And that's and then once we did that, we realized that Ian Affleck has done also the same in a previous work for in a different context, and that actually allows us to think that if you are strongly peaked at the Fermi energy, then you can take this guy out of the integral and fix it that, and then you go back to the trick. And so that was our small contribution. That was hard, but that was simple. And with that, you can actually compute again a retarded Green's function, which is simple again, or we do have the tricks. And that opens the possibility to compute a whole bunch of complicated systems that previously, transport in complicated systems that previously people had addressed only in the 0 temperature limit, and we can do more. So this is the result of the numerical renormalization group for our system. We have run a lot of things here, and that's a crowded graph. I just wanted to show you another one, which is nice here. So this is the experiment, and this is our, but then unfortunately we did the wrong thing, so, okay, good. So this is the voltage in the dot, so that changes the Fermi energy, and this changes the Fermi energy, and this is the position that changes the position of the Fermi energy. No, the resonance is at the cavity, and this is the same here. So actually, we have the qualitative understanding, and also to a large extent a quantitative understanding of how you can tune different parameters of your system and actually control the interference pattern and change the spin, keep the spin, and move on to a situation where you flip the spin. That's kind of cute. Okay, so I'm getting to an end. I hope to have shown you that non-equilibrium Green's function is a suitable tool to address single particle and many body problems. Green's functions can be computed by several techniques. In single particle, we are a big fan of this one. And in many body problems, the arsenal is smaller. Well, we need more techniques. But so we are working with this. That's good for simple Hamiltonian systems. We are expanding to do other things which we'll be able to tackle more interesting systems. And then I illustrated how to use these techniques by addressing or understanding a quantum antibody problem with interference over a large length scales, right? Large is 1 micron, which is the actual, so agrees with the coherence length. Okay, thank you very much.